All right, here is example problem 4.8 from class 13. It's a 5.8 foot sign. It's a pretty big sign of uniformly density and 250 pounds, and it's supported by ball and joint socket at 8 right here. Right, so that means there's no moment carried here, but it supplies a reaction force in all three directions, and supported by two cables. Determine the tension in each cable and the reaction at A. Boom. So really the loading of the thing is going to be a force of 270 pounds that's acting right here. This is a considerably long problem, so just be prepared. You might want to fast forward through the long and arduous parts. What we will do, though, is we'll create a free body diagram of this, right? Because we want to make sure that we're sticking to what we know here. So here's make the thing a little closer, and let's make a free body diagram. They're not nearly as interesting in 3 dimensions, but we'll draw it as best we can here. So acting right here, and we can call that point G, and that's going to be W, that vector coming down here. So we're also going to have, and I will do it this way, and we'll default as being positive on all of these, right? So this is going to be RAZ, RAX, RAY. We're also going to have a vector coming this way. We'll just represent it there as that's going to be our F. That's the cable tension. We'll call that CE. And then we're going to have another one coming up this way. That's the other cable tension. And let's call that BD because it's going between B and D. The dimensions, we could probably leave those off in this particular case. Because this is just like the symbol trying to make sure that we're being cognizant of our FBD, that this is what we're declaring that we're going to do. So let me get some things out of the way that I'm going to need to know. I want to get these forces. So in order to get those forces, I need to represent their dimensions of the thing, and the way to do that is to take the cable direction, and I want to go to D from B, so it's going to be D with respect to B, and we're going to go 8 feet in the negative X direction because we're going that a ways, and we want to go upwards 4 feet. I almost had a little Tennessee just peeked out right there. And then we want to go 8 feet in the Z direction, negative Z direction, so negative 8. Okay, and if we get the magnitude of this thing, square root 8 squared, 4 plus 4 squared plus 8 squared, getting lazy here, that's 12 feet. Right. So if we were going to write out the vector for which one are we doing? dB, right? It's going to be equal to F dB, the magnitude, times negative 8 over 12 I F dB times 4 over 12 J plus negative 8 over 12. Whoops, I forgot to write the FBD in there. K. And so what we're left with in terms of numbers are going to be negative 0.6667 FBD I plus 0.3333 FBD J and negative 6.667 FBDK, and I went over my boundaries, unfortunately. And then we had to do a similar thing for CE, right? So C with respect to E, and that goes negative 6 in the x direction, and goes upwards 3 feet, right here, upwards 3 feet in J, and then positive 2 feet over, right? And then our RC with respect to E, magnitude 6 squared plus 3 squared plus 2 squared, it comes out to 7 feet. And so our FCE is equal to FCE, and I don't know, is it useful to be doing this all the way through? I don't know. 3/7 J and 2/7, and that's positive. Yeah, that's positive. Okay. Okay, so we have a negative 0.8571 FCE I plus R 4286 FCE J, and I didn't make it. 0.2857 FCE K. And I should really put the units on there, right? These are all pounds. That's a pound. That's a pound. Okay. Now, what else do I want to do? I'm going to need to get, I'm going to take the sum of the moments about A, right here. Right, that's A, and this is E, and this is B, right? So I want to get, I need when I take the moments and the cross products, I'm going to need E with respect to A, B with respect to A, and G with respect to A. So our B with respect to A is simply 8 times I. Our E with respect to A is going to be 6 times I, right? Okay, we're going A to there, right? And A to there. And then our G with respect to A is going to be equal to 3I plus negative 2.5J. And these are all feet, by the way. I should really put what the units are. So if we were going to take, oh, and by the way, the reaction is going to be RA goes RXI plus RYJ plus RZK, and the other load W right there as a vector is going to be negative 270 J pounds. So if we take the sum of the forces equal to 0, that's a vector. We want to combine, we will take, and we can go ahead and combine everything we know in the I's, right? So that's really going to be FDB plus FCE plus W plus RA equal to 0, right? Those are all the forces that are placed onto this piece right here. But let's combine all the I's in there. And by the way, let's see. So the we have a negative 0.6667 FBD, and we have a plus negative 0.8571 FCE. We have nothing in the X direction in the W. And then so we add in our X. And we are assuming this is positive. We assumed all of these are positive right here. So that's I. Plus the J, we systematically come here and we go, okay, so that's 0.3 times FB, and that's positive, 0.3333 FBD. And then plus this guy right here, and he's positive, 0.4286 FCE. Now the weight, now this one does have a negative right here, so it's negative 270, and then we also add in the ry plus ry, and that's j. Now we have to have add in all the k's, and so the k, we have a negative 6667 FBD, and here we have a positive 0.2857, oops, and that's an FCE. Nothing in the W is in the K, and then we add in an R, A, Z. It should have been R, A, Z. These should have been A's everywhere here. If I was going to be consistent with things, one right here. R-A-Y, R-A-Z. Okay, and that's K. And for this to be equal to 0, each one of these individual ones has to be 0. So there's really 3 equations right there. But we still have 1, 2, 3, 4, 5 unknowns. Right? Anything else? No. So we take the sum of the moments about A. And it equals 0, but it also equals the sum of the R crosses F plus all of the MI's. Now in this case, there's no moment on this point right here, so these are going to be 0 right here. But that's just because of the nature of this joint right here. It doesn't support a moment, so there's no reaction moments in there. And so I'm going to have to go to another piece of paper pretty soon because this is long. But let's write this thing out first. So let's go one by one. Let's go to this guy first. He's going to be the R, B with respect to A, crossed with F, B, D. Right there, right? Here's the position vector, comes to right there. Right? If we could, we're not going to draw it in there, but we could draw, that's the position vector B with respect to A, and it's crossed against FBD. Then we have the RC with respect to A, crossed with RFCE, right? So this is the position vector right to there, and it gets crossed with there. Then we also need to have this position vector that's coming down to there needs to go to G. So it's RG with respect to A crossed with the force of the weight. And then lastly, or do we have a lastly? Nope. There's no other moments on there. So in order to do this, I'm going to go to another sheet of paper. So let's make my matrix. Do the matrix out. I'm going to go I, J, K. This is the matrix that's going to represent this right here. So that position vector, if you'll recall, for B with respect to A, B with respect to, where'd you go? B with respect to A. B with respect to A. 8. No. Oh no, it's just 8 right there, right? 8. Yeah. Okay. So 8 and 0, 0, and then the force of B with respect to A, that's all of these right here. So that negative 666.333 and negative 666. So negative 0.6667. I'm going to go F. B, let's see, this is FBD, and then 0.333, I should have left room, and then negative 6667 FBD. Now I got to do this one right here, I, J, K, I'm not going to cram. I'm going to try to cram it in. And that one is what, 6, right? That was the RE with respect to A. Did I say E? Yeah. What did I do up here? E with respect to A. E with respect to A. And so there you go. And then I gotta go FCE is right up here. So that's a negative 0.8571. FCE, I could have probably just put this onto the outside, right? And 0.4286 FCE, and then 0.2857 FCE, plus, and then another matrix for this guy right here. So I, J, and K, using up the space. Let's see, RGA was negative 3, positive 3 and negative 2.5. And the force was only in the negative 270 direction here. All right, so doing these cross product thingies, a lot of fun, isn't it? For the I, 0 times here, 0 times there, that's fine. J is this times this, and 0 minus 0 times there, right? But remember, for the J one, we have to make it negative right there. So it ends up being a negative 8 times negative right here. So negative 0.6667 FBD J. And then for the K here, we have 8 times there minus 0 times there. So it's 8 times this times K, and it's positive. 8 times 0.3333 FBD K. Going to the next one, I's, once again, 0, 0, J, 6 times this minus this times this, but remember for the J it's negative, so it's negative 6 times 0.2857 FCE J. Now for the K, it goes 6 times this minus 0 times this, so it's just 6 times this times K. So plus 6 times 0.4286 FCE times K, right? But we got to keep going. We got one more to do here. So for the I, this times this, 0. This times this, 0. Great. For the J, this times this, and this times this, right? So that's pretty good. And then for the K, this times this, and that times 0. So it's really just 3 times, so it could almost fit that in there. 3 times negative 270 times K equals 0. Now there's no I's taking place, which kind of makes sense if you look back up here. There's nothing twisting about I. There's no reason for anything to cause a spin about I. There's no impetus. They should balance. It should balance out. So no reason to worry about that. Also, I pass everything that's in I right here. All the forces in I all pass through A anyway. So getting the J's together. All right. If we just, I'm just going to say what is J right here. And I go if we look and we get those together, we have the negative and negative, so it's 5.333 times FBD, right? This J over here, now this guy is negative, so we had negative, and that turns out to, when you multiply those, is 1.714 FCE equal to 0, right? So there's one equation. And then for the K's that are located up here, if we put these guys together, we have 2.667 FBD. And then we put these together for the K, so it's going to go plus 2.572 FCE, and then we also have this guy, and that's going to be a negative 1080 equals 0. So here's one equation, here's two equations. What I did is I solved for FBD, right? So I found that FBD was going to be equal to 1.714 divided by 5.333 FCE. That comes out to 0.3214 FCE. And then I can put this back into here. So I shoved him back in and said 2.667 times 0.3214 FCE plus 2.572 FCE minus 1080 equals 0, or I could just say that it's equal to that. One step would have been fair. FCE is therefore 315 pounds. I put that back into here, and I get FBD is equal to 101.2 pounds, right? And now I have these two tensions. Now I can come back over into here and find, because I have these tension and reaction, tension, tension, reaction. Find out what all the reactions are at A. It's very similar to what gets done in 2 dimensions. It just has to be more systematic to try to keep track of everything. So from my eyes, I say negative 0.6667. So I will try to fold this so you can see it, although I'm going to use the back of it later, so fold the back of this right here so you can see right here. Then I'm plugging those back in. That's the BD, so that's the 101.2 plus negative 0.8571 times my 315.0 plus my RAX equal to 0. RAX is equal to 337.5 pounds. Because J, and you have 0.3333 times our 101.2 plus R, is that a 0.4286 right here, and times 315.0. Then we have to also remember, okay, now we have the plus RAY, and then minus 270 equals 0. And our RAY, it ends up equaling 101.3 pounds. It looks interesting, but maybe just a coincidence. K, and you have now negative 0.6667, 101.2 plus 0.2857, 315.0 plus RAZ, that equals 0. RAZ turns out to be negative 22.53 pounds. So the answers are FBD is equal to 101.2 pounds. And tension, it's a good thing to write in here. FCE is 315 pounds tension. And then the reaction of RA is therefore going to be 330, let's just round down to 3 sig figs. I plus 101 J plus negative 22.5 K pounds. How are we doing on time? 25 minutes. That's a long problem, but let's go ahead and box this thing out and take a look real quick at the example problem, how it's written in the book. These aren't necessarily the best way, I think, to present this. I avoid using T. Don't like using T for tension. T is a torque. We even use T for kinetic energy and dynamics, or they do. I don't like that fact. But anyway, that's what they've done, and they kept it as fractions to make it a little bit easier for themselves. And then they didn't. Let's see. Here's the sum of the forces. Let's see. Yes, I'm still here. I'm doing office hours at the same time as this, and none of you are showing up. I should point that out. All right, so here we go. They put this thing in here, and then they did the sum of the moments, and they kind of took a little bit of shortcuts in doing it, and they came out with the same answers as us, though, right? And then the same reactions. Double checking at the same reactions, right? The same reactions. Yeah, 22.5, 101.2, 338. So cables, you can't push a rope. You can't push a rope. There you go. Ta-da. Statics. Don't you love it?